So if I keep it this way, is it fine? Whether like you need it just so that
Sir,
I can write something.
okay.
Just
Sir,
use
can you
this.
just increase the zooming percentage?
It will be like it will be gone. It should be this much is fine. Otherwise, I can. One thing is I cannot write, but I can explain. So
Okay, sir, this is fine.
it is okay, visible.
Yes, sir. Yes.
Yeah, so that I can just write.
Okay. Yes.
Uh,
Sir, I seek your cooperation. Can we record your session?
yeah, no problem.
Okay. Thank you so much.
No. Yeah, should I start? All the participants are here, or we
Yes,
wait?
sir. You might start.
Okay. Yeah, I thank Dr. Shailendra for asking me to take this lecture, and thank you, the Engineering College management, for conducting this workshop and having me as a resource person. So, my topic, as I've already been told, meta-heuristic optimization and its application to electrical engineering. This is a more general topic. This will be like meta-heuristic optimization is a broader field which is applicable to any of the fields. So optimization basically is it is completely interdisciplinary. It can be applied to computer science, applied to materials, electrical, electronics, mechanical, civil, chemical, physics, anywhere you have some problem of optimization, you can apply these optimization techniques. So I thought this would be a, great topic for giving a lecture on, so that my aim is that you people, whosoever the audience are, whether they belong to electrical or any other field, so this will be of some delta x addition to your knowledge, whatever you have, and you'll be confident enough to apply the meta heuristics in your research, whatsoever you are performing. So let me just move on to my topic. So let us first understand what is optimization, and then we will further move into our topic. So yeah, ma'am, my time is up to 3:30, right? So 1.5 hours I have.
Yes, sir. Yes, sir. Sir, actually, the last 15 minutes is for the question and answer
Okay,
session.
fine. 3:15 I'll finish. Not an issue.
Okay.
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 So let us first just briefly for 5 minutes let us discuss about optimization, and then let us just take some simple example and understand what is optimization and how the optimization process we generally utilize. So just as a definition, it is a process of making something as good or effective as possible. That means what you want to make something like it should be as good, like as good as or effective. So that means always like minimum or maximum you generally call it as. Always minimum is not good, always maximum is not good. So whenever you are selling something, you want to maximize the profit. Whenever you are buying something, you want to maximize the loss, minimize the loss, right? So it's always a seesaw, like either you can minimize or maximize. So overall what our aim is to make it effective as possible. That's what is the process of optimization. So let us just take an example of let us say you want to build a home. So my aim is to build a home in a city, let us say any city. So I want to build a home in my city. Sorry for the bad drawing here. So let us just assume that I want to make a home. So now that is my objective. So my objective is what? I want to make the home with the minimum possible cost. Obviously, anyone's aim whenever you are making home that you will not be, ready to spend as much as possible. You try to minimize the cost. So I have fixed my objective that I have to minimize my cost. The cost must be minimized. That is my objective. Now, minimum cost means what? Zero. But practically, zero cost is not possible. In zero cost, you cannot build a home, right? So obviously, there will be some minimum and maximum limit. Let's say I want to build a home between 20 lakhs to 20 lakhs to 50 lakhs, let us say. That is my minimum and maximum limits on my objective function. So that is my constraint, like one of the constraints that, okay, I have decided that I'm not going to exceed 50 lakhs. That is, let us say, maximum value I have decided. Minimum is okay. Now, how to formulate the problem. Like we have decided that the cost is the minimum, but cost comes from various factors. What are the various factors which influence the cost? Like the land rate. So land rate is going to be one of the important parameter, land rate. And then the next thing it is going to influence is which type of construction you want to make, whether you want to go for a wooden home, you want to go for a wall, how many floors you want to have, how many rooms you want to have. So, and what are the materials you are going to use, and then what is the interiors, what is the furniture, what is the other, like paintings, everything. So those are all the things which are going to play a part in the cost, right? So we have to find out each and every, we have to tune these parameters such that the cost of my home is minimum, and while satisfying some of my constraints. I want to, let us say, my constraint on the land, let us say I want to buy a land. So if I go near to the city, then my cost of land is going to increase. But if I go far from city, land cost is going to decrease. But the thing is that I have to travel more. When some people want to go, like, you can choose an optimum point between these two. You cannot go and build in between in the city center to build a home, because your entire 50 lakhs may not be sufficient to buy the land itself, instead of making a home. So you should choose an optimum point between, let us say, I can you can form a constraint that cost of land should not be, it should be less than, let us say, 10 lakhs or 20 lakhs. So that is my constraint. So the cost of land should not be more than 20 lakhs. So I should decide based on the constraint. I should decide where my land, actually where I should look for a land. And then cost of materials, cost of furniture, cost of paintings, cost of everything should come. And those are all you can decide individual constraints on them. I don't want to spend more than 5 lakhs on the furniture. I don't want to spend more than 1 lakh on the paint. I don't want to spend more than 20 15 lakhs on the cement materials, right? So based on that, you can figure out within those boundaries. You can find out an operating point. Okay, so the end result of optimization is that it is going to give you the material cost this much, and the furniture this much, paintings this much is going to give you the minimum possible cost of your home. The land cost is this much. Overall, if you combine everything, you are going to get a minimum cost of the home. So with this example, I hope you are able to get the sense of what is optimization is about. Now you can apply to your we do optimization in our daily life. Every day we do optimization. Let's say I have 100 rupees in my pocket, so then I will do optimization. I want to have several things. Then what I will do, I will cut down something, I will increase something. Let us say I have 500 rupees in my pocket. Now I want to have food, I want to go to a movie, I want to buy something, some books. So then what you will do, in order to save some money for movie, I'll buy a cheaper brand. I'll buy a cheaper book, so that I can make some additional money, and I will eat some normal food so that I can have money for movie. Or if my food is my priority, movie is not my priority, I'll spend more on food. I'll take a less ticket. I'll go to another theater where I get a lesser ticket, right? So we do optimization in our daily life as well. So optimization is a wider, broader field. So now let us move on to the meta-heuristic optimization, and what it is and how it is going to be helpful in solving these optimization problems. So is my voice clear? You are able to follow? Am I going too fast? Let me know.
Yes, sir. It's yes,
Okay,
sir.
fine. Yeah. Okay. So let us just get some, into some little bit of mathematics here. So I have a objective function like this. Okay, so I would like to minimize this objective function. If I given you this question, what you will do? There is some small mistake. It should be 0.1 into x square. So y is equal to 0.1 into x square. Okay, this is my objective function. So I want to minimize it. So what you will do? Simply you will take y dash, then you will equate to 0, and that is going to be 0.1, like 0.1 into 2x, and x will be 0. So you will find minimum at 0. So that is very, like, everybody have done this maximization and minimization in your plus 2 or in your btech. So everywhere that you can find out the maximum or minimum of a function. So by simply differentiating and equating to 0. So this is fine as long as you have only one minimum. There is no problem. This can be achieved with the differentiation. And Another condition here is that the function must be differentiable. You cannot apply the same rule to the functions which you are unable to differentiate. So if there is differentiation is not possible, then you cannot equate it to zero and find out the minimum here. And the other way of finding the optimum for the same function is what? By using the numerical methods. You have the Newton-Raphson method. So you will take some initial guess, and then you will find out x1. The next value of x1 is x minus f of x divided by f dash of x. Okay, so you will use this formula, substitute this x value and find f of x, find f dash of x. Then again, you will find the updated value. Then substitute x1 here. Then repeat the same process until you reach f of x is going to become 0 and when x1 is equal to x. So there is no further improvement in x. You are going to get the minimum. So that is a standard Newton-Raphson method. So again, Newton-Raphson method is also gradient-based method. Gradient means the slope. So f dash, like y is a function, y dash is what? Is the slope. So you are seeing for a point where your slope of the function is minimum, like 0. So that is what we are trying to do. So this is also a gradient-based method. So it follows the gradient of the problem and it will reach the minimum possible gradient. And then it will get your h1 equal to x. One of the problem with the Newton-Raphson method is here. So here you can see this kind of a problem. This is also a very simple equation only, not too difficult. But still, if your initial guess, the Newton-Raphson method needs an initial guess for x. So without initial guess, you cannot do this optimization. So right, the initial guess, if by chance it falls in this red dot, then it is no problem. You might probably end up with your global minimum. But actually, if by chance you end up at here, anywhere on the other, except for this larger curve, if you are ending up on the other points in this curve, then probably you are going to end up at the local minimum instead of the global minimum because it follows the gradient. So it will follow the smaller gradient instead of going to the larger gradient. So that is a problem with the Newton-Raphson method. So this is very much prone to your initial guess. If the initial guess is correct, then it will definitely, it is a faster method. You can get a good, exact minimum without any problem. But if the guess is not correct, then definitely you might end up with the local. Now, if you go for a, even further, it will be y equal to x into cos of 2x. So again, it has so many local minimums and only one global. So you can see if you go on taking the guesses, so only let's say 10% the probability that you might get an initial guess in this part. So the rest of all chances there you are going to end up at the local minimum. So I don't want to end up at the local minimum. I want to go to the global minimum because local minimum is I'm getting the minimum point, but this is not the actual minimum. Let's say if this is going to be corresponding to 20 lakhs and this is corresponding to 30 lakhs, so I'm losing 10 lakhs because the algorithm is unable to convert to the global minima. So that is going to be the effect of the local minima here. So now if you go for a further little bit difficulty, if you just increase the dimension of the problem by 2, so now I have a function with 2 variables and one objective function. Now I have a surface like this, so I have a one global maxima, one global minima, and several local maximums and minimums are possible. So it is going to be very, very difficult with the regular numerical methods to solve this kind of problems. You have to go for partial differentiation, then form the Jacobian matrix. So as the number of variables are going to increase, the size of Jacobian matrix is also going to increase drastically. The Newton-Raphson method, the number of computations required and the size of Jacobian matrix and inverse of Jacobian matrix, they are all going to cost a lot because I have a function like f of x divided by f dash of x I have to. So this f dash of x should be inversed, like f dash of x inverse into f of x. So this Jacobian is big and inverse of Jacobian is also going to further bigger. So that is going to cost a lot of computational burden for your optimization. And moreover, the function must be differentiable, then only this is possible. If the function is not differentiable, then it is not at all possible. So now in order to solve all these problems, let's say the researchers have come up with the topic called the meta-heuristics. So what are these meta-heuristics? So the definition says that meta means beyond or above, heuristic is to find. So in computer science, if you might have studied your data structures course in your UG level, heuristic is basically is a process of guessing. Okay, so how you guess, you go to a point and you guess that the direction should be this way, the direction of movement should be this way. So that is basically a simple heuristic. So by just instinctively we are going to move in the search space. But meta heuristic means it is just beyond or above heuristic. That means what? It's simply not searching, but it is searching with some higher level of thinking, that where you are going to apply some logic to search. It's not simply searching, it is going to be applying some additional tools or additional mathematics to solve some problem. That's what is basically the meta heuristics is all about. Okay, so this is a very beautiful definition. I really like this definition because this summarizes entire what are the things, aspects of a meta heuristic algorithm, and what are the different things which are involved in the meta heuristic algorithm. And a simple, like, one sentence actually is going to give us everything about the meta heuristics. So it is formally defined as an iterative generation process. So it is a logic generation process which guides a subordinate heuristic by combining intelligently different concepts for exploring and exploiting the search space. Learning strategies are used to structure information in order to find efficiently near optimal solutions. So this is a basic definition here. Let me just explain here clearly what it is. So it is defined as an iterative process. So one thing what is clear here is that it is an iterative process. Just like your Newton-Raphson method, we are also going to go for iterations. We are going to go for iterations, and which guides a subordinate heuristic. So whatever the heuristic we have in the present process, present time instant, that is going to be guided. Okay, by combining intelligently different concepts. So it's not simply guided like you go in this direction. It's guided with intelligently different concepts for exploring and exploiting. So I'll talk about this exploration and exploitation in a different slide. So exploration basically it involves the process of exploring the entire subspace. Exploiting is where you are going to exploit a particular local search area where you feel that the global minimum possibly exists. Okay, so I'm going to talk about these things in a few minutes later, that what are these things and how these things are going to impact your search process. So for exploring and exploiting the subspace, learning strategies are used to structure information. So we are going to structure the information in order to find efficiently near optimal solution. This is also a very, very important statement, which is going to find, we are going to find efficiently near optimal solution. Okay, this is the common advantage and disadvantage of this meta heuristic algorithms, that we are going to find the near optimal solution efficiently, that is advantage, and you are going to get the near optimal solution. So the solution whatever you are going to get, there is no 100% guarantee that you are going to get the global optimal solution, but you can say that it is almost close to the global optimal solution. So you may not get 100% global optimal, but this can give you an efficiently almost close to optimal solution, right? So that is what is the basic definition it says. So now let us see what are the characteristics. So the characteristics include, the meta heuristics are strategies that guide the search process. So as I told you, we are going to guide the search process. The goal is efficiently explore the search space in order to find the near optimal solution. So either optimal or near optimal solutions. And techniques, these are basically process to complex learning procedures. So there are wide range of I don't know how many thousands of algorithms available in literature, that they are just starting from simple local search procedure to complex learning processes. So this include complex learning processes as well. And these algorithms are approximate and usually non-deterministic. So this is also very, very important. So you cannot 100% claim that the solution whatever you are going to get from these meta heuristic algorithm is 100% globally minimum. So that is approximate solution you are going to get, and these are not usually non-deterministic. So non-deterministic means these are basically stochastic in nature. Stochastic. So what is stochastic? Stochastic means it is basically probabilistic. We cannot 100% be sure of what is going to happen in the next time. So that means that non-deterministic situation means you are not, you run the program for one time, you may get as one answer. You run for one more time, you are going to get different answer. So that is the point of this non-deterministic concept here, that if you know, it's not simple x plus y is equal to 2 and substitute x and find y. So just always you will get same answer. But for non-deterministic situation, you might get a different answer when you solve it for the second time, because of the different initial guesses and different search process we are going to employ. So that is the concept of your characteristic of your meta-heuristics. Now, simple. There are several classifications are there, but as far as like I have only presented two types of classification. One is a single solution based, other one is a population based. So single solution based means you are going to take only one solution at a time, and you are going to iteratively move it through the search space and find out the global optimum. In the population based, you are going to take a set of solutions in the search space. So let us say this is my search space, this is my x variable, this is my variable. You're going to take a lot of agents, search agents, and these agents are going to move in the entire search space, and they are going to search for what is optimal value of x and y, so that you are going to get your objective function minimum. So few algorithms include the genetic algorithm, particle swarm optimization, gray wolf, cuckoo search, firefly, pigeon inspired optimization, like flower pollination. There are so several, like I don't know, if I start naming the algorithms, it takes 2 3 hours to complete all the list. It's so big. There are maybe thousands of algorithms available, right? So this is a general classification. So you might find in the literature, you might find the different types of classification also you can find in your literature. So how to formulate the problem? Now let us just take the same example of your parabola. Okay, so this is my parabola. So this is my parabola here. Okay, so this is my x and this is my y. So now I want to apply meta-heuristic algorithm to find out what is the global minimum for this problem. Okay, so I have an equation y is equal to, let us say, x square directly, 1 into x square. Let us consider that. Okay, so this is not working properly, but okay. So now what I'm going to do first is identify the decision variables. How many decision variables I have? I have to find x. X is a dependent variable here. Okay, x is my dependent variable, x is my independent variable, y I have to find. So only I have one variable, so I have to identify. So this x is my dependent variable x, and define the subspace. Like I cannot go up to minus infinity to plus infinity. I have to define the search boundary. That, okay, I want to search my x between these two bounds. Let us say minus 5 to plus 5. Okay, these are my search boundaries. And form an objective function. We already have y is equal to x square is my objective function. Define constraints. So I don't have any specific constraints here, but I can go for a constraint like my y value should not be more than 1000, something like that. I can go some constraint if I want, I can put. Otherwise, if you have any constraints, you can put. Otherwise, you need not to put any constraints. So if you don't have any constraints, then it is called unconstrained optimization. If you have some constraints, then it is called as a constrained optimization. Now you're supposed to apply your optimization process. You have that slide. So now how the meta heuristic, we have formed the problem. Now how to apply this meta heuristic algorithm to solve the problem? So first thing is you have to define the size of population. What is the size of your population? How many search agents you want? Okay. So let us say usually we take around 20 to 50. So let us say 20 search agents I have to. And if you have any algorithm specific parameters like maximum iterations, some constraints for that algorithm, so that you have to define. And then first thing is what you need to do, you have to generate the 20 randomly possible solutions in the search space. So this is my search space. X is from minus 5 to plus 5. This is my search space. So I'll take 20 samples in this search space. Okay. For these 20 samples, I'm going to find out the fitness value. Fitness value indicates your objective function value, y is equal to x square. Substitute these 20 values in this x. Then you will get a y values of 20 y values. Okay, so you will get a matrix of y 1 by 20. Okay, 20 y values you are going to get. Then find out the best value. Out of these 20 values, you find out which of the solution you are going to get the minimum. Global, like which is the minimum possible solution in this 20. Then corresponding to that y, whatever the value corresponding to in the x matrix is going to be your G best. The position, whatever you are going to get corresponding to the minimum value of y here is going to be your G best, global best position at so far. And based on this global best position, then you are going to update the position of other agents. So based on this present position, you are going to update the positions of all other 20 variables, all other 20 points here. Okay. And then once the positions are updated, you are going to repeat the same process. You are going to repeat, go for again 20, solve for 20 times what is y, then find out the global best out of the 20. If it is better than the previous value, then overwrite. If it is not, then keep the previous global best as it is, then update the positions, then repeat the same process until you're exhausting the maximum iterations. Or the second thing is you might have some tolerance. Let's say I have the answer. I know that x is equal to 0 is the solution to this problem. That once I reach x is equal to 0, near to 0, let's say I say 1 into 10 power minus 3 is my tolerance. So once I reach this value, objective function value, then I can stop. So that way I can either stop or I can go for until the end of maximum iterations. Okay, so this is a simple mechanism for applying the meta-heuristic algorithms, how these are these are applied. Now, as I told you, uh, there are two important aspects. One is this exploration and exploitation. I told you that I will discuss it now. So the exploration part is to be performed in the beginning to explore the entire search space and avoid trapping into local optima. So we have to explore the entire search space effectively first to avoid trapping into the any local optimum, and exploitation to be performed after certain number of iterations for effective search near the possible optimal solution. So I have some explanation for this, a simple example that I am searching for my, let us say, a book in my home. Okay. In my home, I have 4 rooms, let us say. 4 rooms I have. So I forgot in which room my book I have kept. So at the beginning, how you will search? You will search all the rooms equally. You go to this room, you will see like you will see this room, you will see this room, you will see this room, you will see this room. Okay. But after some time, you realize that you have never come to this room. You can see everything clearly in this room. Only bed is there, only one table is there, so there is no possibility that book could be here in this room. So I'm going to eliminate this room. I'm going to eliminate this room. I'm going to eliminate this room also. Now I figured out that my book should be in this room only. Then what you will do? You will search this room extensively. You will search everything. You will just remove the bed sheet. You will remove the, move the sofas. Everything you do to find out the book in this room, right? So the first process, what we did was the exploration process. That we simply searched the entire room so that to make sure that the book is not there in these rooms. Then after some time, then we figured out the no, this is the probability of having a book in this room is more. So now I'll search this room effectively. So near optimal solution, you have to search effectively to get the global optimal solution. So that's what is the exploration part. So any optimization technique we are going to utilize, that must be effectively balance between the exploration and exploitation. So you cannot skip the exploration part. If you don't do the exploration, if you just only search in this room, you might end up in the local minimum instead of you have not even looked into the other rooms. Okay. The second thing is exploitation. If you do more, like you do exploration more, then you, even though you reach here, but you may not get the 100% global optimal solution because you wasted so many iterations in searching the in all the rooms instead of searching in the actual position where you could get a better solution. So the optimization process must be balanced between the exploration process. Okay, so is this clear? Any doubts till now?
No, sir, you made it very clear.
Okay. So now what are the advantages now? Like why we need to go for meta-heuristic algorithms is that these are general applicability. That means these can be applied to any type of problem where you need not to have any specific mathematical model. They need not to be differentiable. They need not to be continuously defined in the range. Range. You can have some infinite values also. We can have poles in between. So that is this meta heuristic can tackle all those things because this is completely random search process. So if there is some place where the function is not defined, you can simply ignore that particular point. You need not to search for that point. So that way you can apply this to any type of problem, and you can apply for the black box type of problem where you don't know what is inside. Let's say I have given you a function that takes some x and y values and that will give me some z. I don't know what is there inside. Still, I can apply meta-heuristic algorithm. Okay, so I need not to have worry about the mathematical model of this function. As long as it takes two variables and gives me some the function value, I need not to bother about what is there inside this box. Okay, so I need not to have a problem equation, problem definition. We don't bother about that as long as you have defined boundaries for the search space. And in that boundaries, if you just supply the value of x and y and you are going to get z, that is sufficient for us to apply the meta-heuristic algorithm for the problem. And obviously the computational time is going to be less for highly complex problems. So you might felt that okay, for finding y equal to x square you have to do so many computations, you have to find 20 solutions every time iteration, you have to do so many iterations you are supposed to perform. But when you compare the same amount of computational burden for a highly complex problem, it takes very very less time. Okay, Newton-Raphson method, as I told you, computation of Jacobian and inverse of the Jacobian, calculating inverse, it takes a lot of time. So it takes less amount of computation time when you go for the highly complex problems. And other is it is these are very easy to implement. There is no difficulty. There are several papers available, several programs available in the internet. You can use them to modify to your requirement to apply to your problems. So what are the limitations? Now let's not go ahead of ourselves and simply forget that this you cannot talk about all the good things. Let us talk about the bad things also. So not so bad, but these are the limitations, some limitations. So again, theoretically, you cannot prove the efficiency of these algorithms because of the nature. As of now, maybe in future you might get a proof for the efficiency of these algorithms as well, because these algorithms are stochastic in nature. There is a randomness included in this algorithm. So once you have a randomness, you cannot guarantee that your solution you are going to get is going to be minimum. So the efficiency cannot be proven. But what usually studies rely on the empirical results to prove the same. So efficiency, in order to prove the efficiency, we rely on the empirical results. So empirical results means experimental results. We are going to run the same algorithm for 100 times and we are going to find out the mean value and average value, like mean value and the variance, to prove that your algorithm is consistently getting the same answer even though you run 100 times. Okay, so that is a good enough proof that the algorithm is working. Okay, otherwise if you know the actual answer you can prove it. If you don't, like in real world we don't know how much cost my home is going to be, so whatever the cost you are going to get should be believed to be the minimum. But if you can get the same cost or near about the same cost, if you run the algorithm for multiple number of times, you can be more or less be sure of your optimization, like the solution as a global optimum solution. So each meta-heuristic algorithm has its own set of advantages and limitations that makes it more suitable for a particular kind of application. So the finding best suited algorithm is a challenging task. So there are several algorithms available. So finding the exactly what algorithm suits your problem is also a difficult task. So you have to understand the problem dynamics, you have to understand the algorithm dynamics, and you have to match both. So if your problem is having several local minimums and it's a multi-model problem, so in a multi-model problem you have to go for a solution where it doesn't follow a single solution, where it explores more, because it is a possibility that you might end up a local minimum. More chances there. In order to avoid that, you have to go for the algorithm which doesn't follow a single solution. It will exploit me. The algorithm should explore more, exploit less. But if you go for some other problems where you have only, that you have a probability, you are probably having simple minimum, single minimum, then you can go for a more exploiting algorithm than the exploring algorithm. So you have to tune your parameters such that your optimization solution is going to be achieved with the reasonable computational efficiency. So let me just quickly discuss one algorithm which is called as particle sum optimization. Then once I discuss the algorithm, then I'm going to just show you the program and just a graphical understanding of how the optimization actually works in real sense, and how the movement of the updation of the positions of the particles, how the objective function value is going to be minimized. So let us understand. So this is based on the movement of intelligence of swarms. Like usually, people will combine this algorithms with some species, some natural nature inspired algorithm. It's not required to attach anything towards the some nature related concept here, but the mathematics itself sufficient to prove that this is. So PSO, this applies the concept of social interaction problem solving. So this is developed in 1995 by these two people, James Kennedy and Russell Abraham. So it uses number of agents or particles that constitute a swarm moving around in the subspace looking for the best solution. And each particle is treated as a point in an n-dimensional subspace, which adjusts its flying according to its own flying experience as well as the flying experience of other particles. So let me just show you the equation here, that this makes things more clear here. So let me just explain first, then we'll go. So basically, what this flying means, the updation, like basically in the present iteration, whatever the value we have, and when you go for the next iteration, so that movement from present iteration to next iteration is called as a flying. So this flying is basically adjusted based on its own flying experience, based on whatever the best it has achieved so far, and based on the what is the global best of the entire population. So it has two bests. One is its own personal best, other one is its overall global best of your entire swarm. So each particle keeps track of its coordinates in the solution, which are associated with the best solution, and that is called as the personal best. And another best value is tracked by the PSO, that is called as the global best. The entire solution, the solution whatever we are achieving, that is called global best, and its own personal best, whatever each particle is going to achieve, is called as a P best. The basic concept lies in accelerating each particle towards P best and G best locations with a random weighted acceleration at each time step. Okay, so that is basically given here. So this is the present position. So first iteration, we are going to define this randomly. Let us say I have 50 particles. So all 50 positions I have defined randomly. And the next iteration, P plus 1 position, is going to be the previous positions plus some velocity. So even the name V itself called as velocity, but it is just a simple addition of some x distance only. It's not literally velocity. It is just some adding component to the distance. So how this is calculated? This is calculated by using this formula. So here you can see this is xid of particular position of the particular particle, and this is the personal best of that particle. So the difference between present position, personal best position is added to the velocity, and the difference between present position and the global best position is again added everything. And this is the inertial weight, which is going to be kind of a balance between the exploration and exploitation, that how much should be the effect of previous velocity on the present velocity, that we can find out from here. So VID is the previous velocity, present velocity just multiplied with some inertial weight, and the overall thing, whatever you are going to get, you are going to add it to the present position, so that the updated position is going to be found out. Okay, so let me just stop here, and let me just show you the same thing in the program. Is the screen visible? Yeah, is the screen visible? MATLAB is visible? Okay. So here I have a function which is called as Achille. So this is a test function called Achille minus 20 into this function whatever is written here. So just and a text function called Achille which has several local minimums. So this is a program for the particle sum optimization. This you can find in several internet sources are available where you can download this program. So this is checking for the boundaries for the function and then finding out the function value and then checking for the boundaries on the function value, and then we are updating the present particle best here, and then we are finding the maximum of all the present like particles and then updating the global best here. And then this is a linearly decreasing inertial weight we are using here. Instead of going for a constant inertial weight, you can go for linearly decreasing inertial weight also. So the velocity, whatever the equation I have shown here, you can see the present p best position minus present position, g best position minus present position. So we are finding out the velocity, checking the limits of the velocity, then we are adding the velocity to your actual particle position here, and then we are printing the g best values in the screen and also the g best, whatever the global best we have achieved till now. So just graphically, let us see how it is going to look like. So this is my objective Achille test function. These are all my particles which I have distributed randomly in the search space. So now in the initial iterations, you can see these particles are randomly moving in the entire subspace. You can see we are searching for the global best. So all particles are just kind of in the same shape of the objective function. That means we are searching the entire region basically. Now as the iterations are going on, you can see the global best value we are getting almost close to zero here. We are not yet zero, so the whatever one single solution is at the bottom, the global best is here. So we are getting almost near zero. But slowly you can see all the particles which are there on the top are slowly diminishing, and you can see the thickening of your this cone shape where you are getting more and more particles started to accumulate. That means these are all particles now following the global best position. So now you can see the cone size is little bit smaller. So you can see all are more or less going into this. So if I have set as tolerance of 10 power minus 3, the algorithm would have been stopped, but I have put an absolute 0. So as far as the MATLAB term, absolute 0 indicates that 10 power minus 15 is the absolute 0. So this fourth graph is here is just a zoomed version of this last 10 iterations, so that you can see, because here it is not visible. I made it in a smaller separate graph so that we can see that it is still decreasing. So now you can see all the particles are more or less started to condense into the final this part of this cone. So some particles which are moving around still. So after some iterations, you can see that all the particles are going to come down and settle at the final global optic. So let us see. There are still some particles which are roaming. So you can see the present best position is 10 power minus 10, 10 power minus 11, minus 12. So once we get 10 power minus, you can see all the particles have settled at almost close to zero. So 10 power minus 13, still it is happening because it is not visible because it's a very small space. So 10 power minus 14. So that's why it is not visible. But so now we can see the MATLAB has stopped. So we got 10 power minus 0, 10 power minus 16. So by this way, we can see that graphically that how the particles are going to move in the subspace and how the optimization is actually going to happen and how we get the global optimal value. So now we can see with confidence that your PSO was able to get the global optimal value because we know that at 0, 0, I have the global optimal solution. And if you just look at the LG1 and LG2, you can see the 0, 0 and your objective function minimum value is also 0. So that we are able to achieve. So that's how the algorithms are usually going to work. So any doubts in this? I hope you are able to get a taste of how the optimization looks like. Yeah. So now let us move on to the other algorithm. Just I'll just explain briefly. So this is a genetic algorithm. Basically, this is a one of the like fore and front runner of this type of algorithm. So this has been invented in maybe 1960s. So from there onwards, it just is a robust, very highly efficient algorithm. Still, till now, people are using this algorithm, and this actually works on the concept of survival of fittest. So instead of moving the positions, updating the positions, what we are going to do in the genetic algorithm, we are going to first, just like we are going to randomly initialize, we are going to have, let us say, 100 people are there. How this is going to work? So in the 100 solutions, whatever we have, we are going to rank them in the fitness. So fitness means the minimum. Let us say you are minimizing the problem. The smaller the objective function, the fitter the solution is. So you're going to rank your solutions, or basically sort your solutions from minimum to maximum, and we are going to remove last, let us say, 20 solutions from the batch. So these 20 are removed, and then you are going to take the first 40 or 20 solutions. You are going to make them as parent solutions, and you are going to combine these two solutions to generate one new solution, and that new solution you are going to put back into the list. Okay, so basically the concept is what, as the children are always more intelligent than the parents. Usually that is happens in your in our human like human biology, whatever you call it as. So the children tend to be more intelligent. So if you take the top two positions and you're going to mix their chromosomes, basically everything, it's in the biology terms here, chromosomes. So mix their chromosomes, then you are going to get a new chromosome, a new solution that is going to be much fitter, right? So you are going to remove last 20, generate 20 from the existing population. From the top, you take the parents and you mutate, and you're going to generate new solution. That those things are going to be installed back into your solution. Then rank again, find out the solution, then rank again the list into the from top to bottom, again remove last 20, then repeat the same process until you get your entire population at the same intelligence level or same fitness level. So that is going to be your overall best solution, whatever you are going to get by using the genetic algorithm. So now we sort of understood what is the how the meta-heuristic algorithms behave, and how what are the things are there while using the meta-heuristic algorithms, and we have seen one or two types of algorithms also we understood. Now let us move on to the application part. Like, what are the areas in which these are the only few. I cannot cover all the areas in one lecture, but whatever the areas I come across, I try to showcase here as an application part. So I think most of you might be aware of the selective harmonic elimination concept here. So whenever you are going for a multi-level kind of a setup here, where you have three cascaded switches connected in series. So this is the output voltage waveform when we go for fundamental switching. So there are two switching scenes. You can go for high frequency switching, you can go for low frequency or fundamental frequency switching. The high frequency switching is going to give you PWM output. The PWM output, the harmonics will be very high, harmonic order will be high, so you can easily filter out. But the problem with that is going to be the losses. The switching losses will be more. So if you go for low frequency switching, then the possibility of getting the lower frequency, lower order harmonics in the system is more. So you will get, definitely you are going to get the lower order harmonics in the system. So our aim in the selective harmonic elimination to eliminate the lower order harmonics, right? So so the bridge one is going to produce this output, two is going to produce this output, three is going to produce this output, and finally if you combine these three together, you are going to get this kind of an output of the CSB MLA under fundamental frequency switching. Now, how to form the formulation? So these are the selective harmonic elimination equation from the Fourier series. So if you just cos theta 1, theta 2, theta 3, if you add these three, these are the fundamental components. So 3 times of modulation index I want to get from the fundamental, this from the first equation. I want to get the constant output voltage corresponding to this modulation index. And the next two equations, whatever I have, phi theta 1, phi theta 2, phi theta 3, 7, 7, 7. So these are the two equations which I'm going to utilize to eliminate the fifth and seventh order harmonics from my system, right? So because I'm not eliminating third harmonic, because in a three-phase system, I need not to eliminate a third harmonic. But if you're going for a single phase system, then you can take, instead of 7, you can go for a third harmonic. So this is my object. These are my objective equations. Then I can formulate an objective function like this. So three objectives. P1 is just take this 3m to this side and equate it to 0. So my objective function is minimizing the sum of these. So I want to get as minimum close to 0. The total sum of these three must be equal to 0. Since actually it is a multi-objective problem, what we are doing, we are combining those three into a single objective, and we are finding the minimum value of the total objective. So if I get a f value as 0, so that clearly indicates that I'm getting this 0, and this 0. So overall my objective function is 0. And the constraints will be what? Your angles, whatever the angles you are going to find, theta 1, theta 2, and theta 3 must be between 0 and pi. So there are several research papers available on the same multi-object, the selective harmonic elimination optimization. You can find a lot of literature. So most of the algorithms were applied. You can develop your own algorithm, or you can modify the objective function here. You can go for the weights. You can add some additional weights to this objective function, w1 into p1, w2 into p2 into p3, to prioritize your objective values. So that you want to have more priority to first one, so have more weight to first one and less weight to second and third one, so that your objective function is satisfied accordingly. Okay? So that is the first application. Second, for drives part here, you can utilize your meta heuristics to compute the objective function. Like here, the gains of your kp ki, to optimize the gains kp and ki in pi controller. So tuning of the pi controller is also one of the important research area, where you can tune your like these speed controller by using different methods. Some people may call it a Ziegler-Nicholas method, or some people develop the state space model of your entire inverter, motor, controller. So you have to make and then plot the Bode plot, make the transfer function, develop the Bode plot, then find out your kp and ki such that your gain margin and phase margin are positive. So that is one of the approach. The other approach is that instead of going for all the mathematical models, you can run online optimization. So you can take the error value, omega reference and omega actual value, give it, compute the objective function. The objective function can be of your choice, where either that can be, let us say, your objective function can be, so this is my response. So my objective function can be the maximum peak overshoot. I don't want to have any peak overshoot in the speed. Or my objective function can be steady state, minimum steady state error. Or my objective function can be fast response, quick dynamic response, like rise time should be smaller. So you can choose any one of the objective function you want to have, and then use the the meta heuristic algorithms to give kp and ka as the variables. Then for a particular of kp ki, then find out the objective function value, then find out the error in the speed, then update the positions of kp and ki, then find out. So finally you can get your kp and ki. Either this can be done online, or this can be done offline as well. So offline optimization is also possible. Here you can perform this optimization and then choose a particular value of kp and ki. This will be overall minimizing your objective function. Then you can simply put that kp and ki, remove this from the real time scenario. Or in the real time means you can just continue the same process in the real time as well. So it's up to you. So these diagrams I have taken from this paper. If somebody would like to go and read more about this topic, you can go for refer this paper to get more idea. So the next thing is you can apply the same concept to the fuzzy logic as well, where you can tune the membership functions. So the membership functions are, fuzzy membership functions are like this, where how to tune the size of this membership function, like what is the distance and what should be the value of this membership function, like for different membership functions. So the width of different membership functions can be taken as your uh, variables, and you can take the overall again speed, peak overshoot, or settling time, or rise time as a objective function, and then you can tune your sorry, this is a pi only. The next is fuzzy. The pi, again I have multiple pi controllers, so you can apply the same optimization technique to work with several pi controllers at the same time. And the same concept can be applied to the fuzzy here. So the fuzzy logic, again, what I was talking there, that you can utilize your fuzzy logic. You can use the optimization technique to find out the width of x1, x2, x3, xn, several membership functions we have. What are the width of the membership functions? You can find out by using the fuzzy logic as by using the optimization algorithm as well. Same thing, fuzzy logic with different like three more controllers we have. Still, you can apply the single optimization algorithm to find out the objective on the global minimum value corresponding to the what is the membership function of the input value. So the other that is the point of the drives. The other aspect is that you can work in this area as well. PV parameter estimation. So PV panel we have. This is a standard model of your PV panel. So we have the current. It is PV source is modeled as a constant current source, and PV PN junction is modeled as a diode, and the resistances, body resistance, RS and RSS are going to represent the recombination loss, and the body resistance are going to be represented by using RS and RSS. So this is a standard PVI, like the PV panel model. But whenever you purchase a PV panel, that parameter corresponding to VOC, ISC, IMPP, VMPP will be given to you. But the values of RS, RSH, and the diode ideality constant will not be given to you. You are supposed to estimate the parameters so that to get the accurate mathematical model of the PV panel. So these are the equations. You can see from this equation, the I is equal to total IPV minus the diode current, and then whatever the current which is going in the shunt branch. So that is the equation here. I is equal to IPV minus this is diode current, and this is the current which is flowing in the shunt branch. So this VT is given by this equation. These are all standard diode equations. This is the diode saturation current, this is the saturation current, this is I naught nominal value, this is the actual value, and this is IPV. So this is dependent on the radiation value. So as the radiation increases, the IPV is going to increase. So that's why it is modeled as a constant current source depending on the irradiation value basically. So in this equation, if you see, we know V, we know I, we know VP, everything, but the unknowns are RS, RSH, and A. So we need to know these things to get your mathematical model accurately for the single diode model. So how to form an objective function? Just bring this I to this side and make it equal to 0. So that's what is the objective function here. IPV minus I naught into this is a shunt branch, and minus I. And objective function is what? The root mean square of all the points on the VI curve. So if you just take a VI curve like this for a PV panel, you have to perform experiments and find out the IV points on the entire this duration. For each IV point, you have to apply your optimization algorithm and find out your sum of, like, for the particular value of RA, RSH, and A, RS, and RSH, you have to find out the error. What is the error corresponding to your experimental result you are getting? So that error, sum of all those errors can be called as the root mean square error for the entire optimization. So where n is the number of experimental data points. So all the experimental data points you are supposed to take. For each iteration, you are supposed to take all the data points for each value combination of RS, RSH, and A. Then find out the error for that is going to be fitness for each of the particle, and then those positions will be updated, and at the end, if this error is 0 for all the data points, it's not one data point, your objective function is error corresponding to all the data points. So if you are going to get the all data points error minimum, that means your mathematical model is close enough towards the actual VI curve of your PV panel. So those values corresponding to that minimum value, RS, RSH, and P will be your parameters for the PV panel. So this is how you can estimate the parameters for the PV system. And then you can also use your evolutionary algorithms for the MPPT. So MPPT, again, you can see the PV, like you most of you might be knowing. So VI curve of a PV panel is like this. PV curve, if you multiply V into I, V into I like that, you are going to get a power versus voltage curve like this. So again, this is an optimization. We have a DC-DC converter here. So if you vary the DC-DC converter duty cycle, you can operate your PV panel at this point, this point, this point, this point for single value of irradiation. If you can operate your DC-DC converter at this duty ratio, you are going to get the maximum power out of it. So again, there is an optimization involved. So you can utilize your evolutionary algorithm by reading the VPV and IPV and choosing the particular value of duty ratio that will control the buck boost converter such that your PV panel operates at the maximum power. That is also an area where you can work to utilize these evolutionary algorithms. And then like again for PI controller based MPPT, again the PI controller gains can be updated. So here it is GA is written. You can apply any algorithm, not only GA, to apply find out the gains of the PI controller and then remove this GA part and simply use this optimal solution KP, KD in the controller, and then you can apply your online mode. So the offline mode, you are going to solve for these optimization algorithms and find out what is the optimal value of KP, and KD, and substitute them in the controller, and then this is over. So you can simply utilize this system for your actual real world applications. So now some little bit of insight into the PV technology industry today. What are the challenges which are there? Just to benefit the people who are willing to work in this PV technology area. That what are the areas in which you can try and look upon to work. So just I'll briefly take 5 to 10 minutes to cover this. So one of the challenge is the cost of PV panels. So this material science people, metallurgy people, to reduce the cost of the PV panels, you can experiment with different PV panel technologies to reduce the cost of PV panel. And usually these are kept in remote locations. So theft, one of the common problem. Theft of modules, cable, other equipment is also one of the challenge in the PV industry. And other issue is the soiling and icing. So in our country, probably icing would not be much of a problem, but soiling is definitely a bigger problem because of the non-proper maintenance of the PV panels. We are going to lose about 30 to 40% of the revenue or the units generated, because if there is a dust settled on the PV panel, then the efficiency of the PV panel goes further down. So already it's already 20% and it goes further down. So then you might not get any proper output from the PV panel. So that is going to, you're going to lose a lot of money. So this is one of the issues which need to be taken care. So in the desert location, so you don't have water supply and soiling, dust storms are going to come and that is going to soil the PV panels a lot. So that is the issue in the desert location. Cold areas, again, snow is going to be a problem, and cement thermal related industry. So there will be dust, a lot of dust in the air in the near areas of cement and thermal area. So there also a lot of soiling is going to occur on the PV panels. Now, what are the opportunities? So you can go for the PV cells with efficiency, higher efficiency, and you can develop new type of modules where you can have less losses, increase the efficiency, increase the decrease the body resistances. So in any way, if you can contribute in this field, you can do this, and you can go for the solar inverters. You can design solar inverters. So already efficiency is about 90 to 95 available. You can further increase the efficiency, and otherwise you can go for some fault tolerant type of inverters, where because of the if there is one leg is having problem, then the other leg should kick in and should be giving your output power. So that will save a lot of time and money for the people. So that is also an interesting area. And this is one of the very important area, PV module health monitoring equipment. So this is where you can work seriously on, because you can see for a 1 megawatt plant, you usually require about 4,000 PV panels. Okay, So if let's say I have 10 megawatt plant or 100 megawatt plant, you can imagine how many number of PV panels and how big the area is going to be. So if there is a particular portion of the PV system is unable to is not generating proper power, so you cannot go on looking for each and every panel to look at where is the problem. So the diagnostics and health monitoring is one of the very important research area that will be directly useful to the industries, where you can develop some technology, you can develop some equipment which will monitor by sensing the signals. If you can monitor the health of PV panel, so that is going to be a very huge impact in this area. Not much in the area of transformers and cables. So protection and switchgear also some part is there. And another important is your SCADA and IoT and data logger. So these are going to be also very required in the PV industry, because your PV plant will be there in the remote locations and your offices will be in the office city. So your data, whatever the PV data you are getting, must be generated, stored into some devices in the data loggers, and this must be sent into cloud through IoTs, and the data should come back to your computers in the office, and you should be able to control your inverters by sitting in your office. Okay, so this is also an important area which people can work. Some auxiliary space heaters, lighting, this is all not so much. So where I have put a star there, there is an opportunity for startups also. You can develop some equipment. It's not going to be too costly. If you're able to get some equipment in this area, then you can develop a startup by utilizing these ideas. In the maintenance sector, so you can develop some robotic cleaning technology, because again you can 4,000 into 100 for 1 megawatt or 100 megawatt plant, you'll get more than 4 lakhs of PV panels. So those many PV panels manually cleaning is out of question. So we should utilize some robotics. So you can develop some robotic application to clean the PV panels. You can go for some, you can develop some testing, diagnostic testing technologies, where due to for lower production. So what is if your PV panel is giving, the PV system is giving lower power production, but if the panels looks clean, then what is the problem? So you should be able to diagnose the problem. So if you are able to develop some techniques to diagnose the problems, that is also a useful thing for the industry. And you can go for some IV curve tracing, check for degraded modules. So if you can find out some methodology to check for degraded modules by using IV curve tracing for different PV panels, that is also a good useful contribution. And the newest or final concept is the thermal imaging. So there will be some hotspots on the PV panels when there is an improper power sharing between the PV panels, or some degraded PV module is there. So there are some thermal hotspots are going to form, and the PV panel is going to become heated, and it is going to produce a lot of less power. If one panel in a series of panels produces less power, then it is going to hamper all the other panels, okay? Because the current has to flow through all the panels in series, so it is going to create a lot of problem. So by using thermal imaging, if you can find out the degraded modules, degraded panels, that is also going to be a good addition to your research. Okay, so these are the areas for the students. If you have some faculty, you can advise your students to work on, so that these are industry relevant, and people, these students who are passing out can be industry ready. They can go for direct their own ventures or their own startup, or they can work from some PV industry directly if they didn't project on any of these topics. So the industry people will be definitely willing to take them. Okay, so I hope I'll end my presentation now. So I hope I have given you some insight into the optimization, some additional insights into the PV industry. So if you have any questions, I'm happy to answer.
Yes, sir. We are now open for the question answer session. Dear participants, you may ask questions. There was a question in the chat box, sir. I'll read it out for you.
Good afternoon, sir.
Yeah, tell me please.
Hello.
Yes.
Yes, I'm
Yeah.
I'm listening.
Yeah, hello, sir. This is Dilip, sir.
Okay.
Sir, actually, I'm working on optimization as the slide you have shown that we are using the PV panel and then we are using the MPPT technique in that. Sir, actually, I have seen many YouTube videos also regarding the optimization. But
Mhm.
the problem that I am facing is that key in every optimization we need the objective function, and with that objective function we are defining the lower and upper limit.
Okay.
Okay, sir. Sir, like I'm going to use the optimization technique for the PV system for the different shading condition.
Okay.
So, sir, I'm unable to find out the objective function what I should be taking. Like I have to have the duty cycle according to my radiation.
Yes.
So, sir, can you help me out regarding that? Ki, how the duty cycle can be the objective function and which parameters I have to consider for
So
defining that?
objective function should be like what is the maximum possible power you can get. That can be your
Yes,
objective function, like maximizing the power, right?
yes, sir, maximizing the power.
So you like basically you are going to take your duty cycle as an input to your MPPT. Like
Okay,
input,
sir.
what is your output of your MPPT? The decision variable is the duty cycle, right? So the only the PV power output, VPV into IPV, whatever you are going to get, that must be your objective function. That you should maximize.
That should be maximized.
Maximize.
Okay, sir. And what I should take the lower and upper limit? Like in every optimization, they are asking for the lower and the upper limit
For the objective function or for the variable, decision variable.
for the decision variable. Like for the duty
So
cycle, it is
no,
0 to 1.
we have that duty cycle we have, but even you can further trim it. You know, zero is definitely you are not going to use. So if you have some, you know, decided some actual some experiments like you did, you can find out what is the probable range. So you can just narrow it down a little bit. Don't take 0 to 1 because it might produce some undesirable results. So then just take some like point 0.2 to point 0.4 or point 0.8, like just vary based on the what type of converter you are using. So choose your bounds.
Okay, sir. Okay, sir. Sir, one more thing. I want to like the PV panel has to be connected with my optimization. Like I'm using the GWO.
Okay.
Like how to connect that, sir? Is there any book there that we can connect the programming with the matter with the simulation part?
But, there is no book, but you can easily write the code. You can run the simulation in the program as well, or you can write an M file in your simulation. So that way you can do. Either you can run the simulation through optimization. So you can just let me show you a simple. But you can run this any particular simulation file here. So T is equal to, let's say, sim of, you can write your file name, some, let's say, file dot slx, okay, and then you can
Okay.
define what search range from what time to what time, 0 to, let's say, 1 second, right? So like this you can write your code. You can search in Google that how to simulate a file from M file. How to run a simulation from M file, you will get a lot of information on it. So this is
O-
a standard way to call a file simulation in a program. So this way you can run the simulation in background. You need not to open that file. This simulation automatically runs this file, and whatever the output it is going to, you can, it will come in the workspace, and from the workspace you can drag your whatever the variable you want to have as a.
o- okay, sir. Thank you, sir.
Any more question?
Yes, so there was a question in the chat box. I'll read it out for you.
Okay.
The question says that which optimization technique would be best for designing control parameters of a time variant system?
And variant system, um, no, actually it's a broad question. Like what type of, there is no specific defined algorithm for any particular application. One has to work with, yeah, yeah, okay. Mhm. Okay. Mhm. Okay. So one way of dealing with that kind of a situation is that you can go for online type of optimization where the parameters are continuously optimized. Okay. Every run, but it requires a lot of computational effort because the optimization has to be done every time. The other way is you can you have like your PI controllers are still be there. You want to go for PI only or some other controllers you want to go for? PI controller is there. So one thing is you can perform different dynamics of your load and dynamics of your system and find out the what is global overall KP and KA which will give you overall best. Like it may not be best in particular sense for a particular instant, but overall it performs better. And the second option is you can go for you can find the PI different types of loads or different types of situations, and then you can train it to ANN, artificial neural network, and then you can apply the ANN to instead of PI controller. If you remove PI controller and use the all the tuned PI parameters, you train an ANN, and then you can utilize artificial neural.
So this will be good for an a system in offline mode. But if the already the system is running, and while the system is running and we are playing with these control parameters, will it not affect the transient?
Yes. It will affect.
It will affect, no?
It will affect. It will affect. But why? That's why we don't generally do online tuning. You can do the offline tuning and use the parameters. Or otherwise, ANN is you can change. ANN is already pre-tuned, so it is based on what are the control inputs. It will give you the better KPI. It will give you the better dynamic performance. So ANN you can utilize online, no problem. But training has to be done offline.
Okay. Okay. Thank you, Dr. Mahesh. Thank you so much.
Thank you, sir. Thank you so much. It was an amazing lecture. It was such a nice that you started from the basics so that we could recall, brush up our optimization techniques, and then you move forward towards application part. We are really honored to listen from you. Thank you so much, sir. For any future events, we'll reconnect with you, sir.
Sure, sure, fine. Yeah, thank you for asking me, and thank you for patiently listening. So,
That was a pleasure, Dr. Mahesh.
Sir, we enjoyed the session.
I just rushed through a lot of things, so hope you were able to get something out of it.
No, it was really great.
It
Mahesh,
was a great session.
Mahesh, I
Uh-huh.
just want to your permission to upload this on the our department YouTube channel.
Okay, no problem.
So
No
all
issue.
these material will be available there as well. Your whole lecture and the discussion, the participants discussion. So
Okay,
it
fine.
will be good for others as well. Maybe.
Yeah, no issue, no issue.
Okay. Thank you, sir.
Yeah,
Thank you, sir. Thank you
Thank
so
you.
much.
Thank you so much, Mahesh.
Dear participants, kindly